In this video lecture, we are going to learn about the moment distribution method. So, moment distribution method of analysis of beams was developed by Hardy Cross in the year 1930. It is a deformation method similar to the slope deflection method, and also it is an approximate method because it involves the iteration process. We can't end the process at a particular stage. We can limit the iteration depending upon the difference between the values. The degree of accuracy of the results obtained by the method of moment distribution depends on the number of successive approximations or the iteration process. Before carrying out the moment distribution among members, all the joints are assumed to be locked, that is fixed, and then released successively. Once a joint is released, the rotation takes place since the sum of the fixed end moment of the member meeting at the joint is not zero. Because the fixed end is released, then there will be an unbalanced moment at a support conditions. How the unbalanced moment occurs? If you consider continuous beams with the intermediate fixed T. Here you will get some fixed end moment minus 30, here plus 30. Here it is minus 40, if it is plus 40, you will have the unbalanced moment of minus 10 kilonewton meter at the joint B. So the value of sum of the end moments will have some unbalanced moment at that particular joint. This unbalanced moment should be distributed and also carried over to the adjacent supports depending upon the support conditions. Because we know the equilibrium, joint equilibrium condition, that is summation of moment at B should be equal to 0. Hence this unbalanced moment should be carried to the adjacent supports depending upon the exact original support condition, and also distributed to the adjacent member depending upon the distribution factor also. Because any at a particular joint there may be two members connected, or there may be three members connected to a particular joint. So depending upon the number of members, the distribution factors will be incorporated. The distribution and carryover is incorporated into the calculation using the calculation of the particular factor. How we can calculate the distribution factor? If the particular joint is connected with 4 members, we will having each member stiffness. Otherwise in beam member we call it as rotational stiffness. Each member has its own stiffness value, that is mentioned as K. With respect to the particular joint, I can mention as KOA, KOB and KOC and KOD. The distribution factor for the member, particular member O2A means we can write KOA divided by summation of all member stiffness, that is KOA plus KOB plus KOC plus KOD. We can sum up all the member stiffnesses and consider it as in denominator to calculate individual distribution factor of the particular member. The distribution factor is a factor used to determine the proportion of unbalanced moment carried by each member meeting at a joint. For the members meeting at the joint O, we will have this type of member calculation. Here I am having some other examples. In this frame, only 2 members are connected at the joint A, so we can have KA to C and KA to B, and the distribution factor is for the member A to B, KA to B divided by the summation of all distribution stiffness values, and distribution factor for AC is equal to KAC divided by total summing of all stiffness values. For 3 members connected, in this case, for 3 members connected, we will have individual stiffness values. If you want to calculate for a particular member, keep the stiffness value in numerator for that particular member divided by sum all the stiffness values. So it will give you a distribution factor. And we already have seen that four members connected with a joint. In this way, we have to calculate the distribution factors for each member. The member stiffness is normally defined as the moment required to produce unit rotation, that is m by theta. In case of axial loading, we normally defined as load per unit deflection. In case of beam, we can rewrite this as moment per unit rotation. So MAB by theta A or m by theta. So the first case, a beam is considered where one end is applied with the moment. It is also otherwise understood with the support A is a fixed, because this A support is having one moment value, and also the far end, this B is considered to be the far end which is fixed. So definitely there will be a moment value at B. So consider a beam hinged at A but applied with a moment M and fixed at B. Hinged support applied with a moment is equivalent to a fixed support. Applying a moment M at A will have some rotation theta A at this point. So we can write the slope deflection equation at A is equal to MAB equal to 2EI by L 2 theta A plus theta B, and the support sinking component I have left because we are going to compare only these three. So you multiply this inside 4EI by L into theta A plus 2EI by L into theta B. So compare MAB with this component only, that is MAB by theta A equal to 4EI by L, which is the stiffness, that is rotational stiffness value. Okay. So in this equation it is clear that MAB equation, and you compare with only the rotation at A. So MAB equal to 4EI by L into theta A. So the stiffness value K for this member is equal to 4EI by L, because we are considering the unit rotation to, so theta A equal to 1. So the moment required to produce a unit rotation is equal to the stiffness or rotational stiffness, so which is 4EI by L. Next one, a beam hinged at both the ends, but a moment is applied at A causing the rotation theta A at A. So here we can understand small concept, that is at A we have the moment M, AB, I can call it as MAB, and we will have some rotation theta here, the span L, and I am going to write the equation for theta. I am going to write the equation for the deflection, which is theta by L. So the deflection is equal to the moment. I am going to use moment area method, that is half into span into moment. The centroidal distance is from B, it is 2/3 of L divided by span into EI. So we will have ML by 3 EI. ML by 3 EI. Okay. Actually I missed some points here. That is, only one moment is applied at this point A, and the other point the moment is 0. So the reflection will be like this. Here we will have some rotation, and the moment value will be here MAB. So we can calculate the slope here. If you mention as the deflection is equal to moment of BMD, that is moment of BMD by EI. The area into centroidal distance is equal to the bending moment. So the area equal to half into span into MAB is the height into, from B it is 2/3 of the L, the centroidal distance 2/3 of L divided by EI, which is equal to MAB L square by 3EI. MAB L square by 3EI, where the theta, if you see this triangle, where theta equal to delta by L. Here it is the delta by L. So MAB L by 3EA. This becomes MAB L by 3EA. Now your theta equal to MAB L by 3EI, and we can form the stiffness value K equal to MAB by theta or M by theta, which is equal to 3EI by L, because you are bringing theta to this side and 3EI by L on the left side. So it is 3EI by L. So finally you have to remember the case 1 and case 2. Case 1, both the ends are fixed, hence K equal to 4EI by L. That is, far end is fixed. The case is far end fixed. If you consider this end as the consideration, this right side end is the far end. The second case, the far end is simply supported condition. Here K equal to 3EI by L. So you have to remember these two formulas for our calculation. Next one, carryover moment. Because until now we are familiar with the distribution factor. The distribution factor depends upon the stiffness value. The stiffness depends upon moment per rotation. The moment per rotation having two cases. One is far end fixed, which is 4EI by L equal to K. Next one, the far end is simply supported, which is 3EI by L. Now the carryover moment. Carryover moment means, if you, for example, if you are considering the problem like this, and considering one end simply supported for better understanding. Okay. This end is actually a fixed support. So definitely there will be some moment. Okay. But this end is a pinned support. Here the moment should be equal to 0. And you are making the joint B, the moment, summation of moment should be equal to 0. with the given loading condition, you will have some unbalanced moment at the joint B. Depending upon the loading condition, you have this minus value and plus value, here minus value and plus value. If you are sum up these two values, you will get some unbalanced of any magnitude. You have to make this joint as a balanced equilibrium condition. Then you have to carry over some unbalanced moment to the nearest point. Here, if it is 10, if it is 10 kilonewton meter of unbalanced moment, you can carry over this 10 kilonewton meter to the support A, because it is a fixed support, because fixed support normally having the moment values. If consider support C, if you are having 20 kilonewton meter of unbalanced moment, you can't carry over this moment to the nearest pin support, because already the pin support should be, the moment should be equal to 0 at the pin support. So no need to carry over the moment from C to D, where the support D is the pin support, because in support D there should not any moment. Already this is the condition to be satisfied. Then there is no point in carrying over the moment value from C to D, because we try to make the moment at D should be 0 and not further carry over and adding the moment at support D. If the far end is fixed, then only the carry over should be done, and if the far end is intermediate, then also the carry over process can be made. If the far end is simply supported, we should not carry over the moment. Then how the moment can be carried over? We already familiar with the slope deflection equation. The first component is 4EA theta A by L. The second component is 2EA theta B by L. We can understand one concept, that is, if a particular moment at A, B is 4EA by L, then the half of the moment is transferred to the support B, because it is 2EA by L. So that is the carryover. That is the moment at 2, that is moment at B, which is equal to moment at A by 2. If you consider any moment value of 20 unbalanced moment at A, you can carry over 10 kilonewton meter to the B. That is the carryover concept. You keep in mind that if the far end is fixed, you can carry half of the moment to the far end. If the far end is simply supported, you should not carry over the moment, because already the support condition to be 0 for the moment values at the simply supported. And also we can carry the moment to the intermediate support, because intermediate support is also considered as a fixed. You can carry the half of the moment to the intermediate support also. The carryover factor is half for the second point. If you consider this is the point of consideration A, then this moment can be carried half of the value to the next support. That is the concept. Here I am giving the abstract that far end is fixed, the carryover factor is half. Far end is hinged, the carryover factor is 0. Next, coming to the procedure of the moment distribution method. First step is to find out the fixed end moment for all these spans with a given loading condition. Then find the distribution factor, that is 4EI by L and 3EI by L for each member. Then finding the unbalanced moment. Unbalanced moment means each span will have the fixed end moment values, that is minus 10 plus 10 and minus 50 plus 50 and minus 30 plus 30. And if you consider this is joint B and joint C, you will have minus 40 of unbalanced moment at B and plus 20 of unbalanced moment at C. That is the unbalanced moment calculation. So each joint should be calculated for its unbalanced moment. And the next process is we can carry over this unbalanced moment to the nearest support, whether it is fixed, it is half, whether when the case of simply supported it is 0. We should not carry over the moment to the simply supported conditions. And add further, then the next step, add all the moments and check whether the summation of moment at the joint becomes 0. If it is not, repeat the steps for the next iteration. Okay. You can easily understand with this simple tabulation. First of all, you make joint representation. We have joint A, joint B and joint C. Joint A is fixed, joint C is pinned, joint B is intermediate. And represent the member, that is A to B. From joint B we have two members, B to A and B to C. And joint C we have one member, C to B. Next, calculate the distribution factor for each member, because the distribution factor is calculated for each joint. Here the intermediate joint is B. We should not calculate the distribution factor for C because there is no member on the right side and also there is no member on the left side of the A. So the only possible distribution at B. So calculate the member B to A, which is 4EI by L because it is far and fixed, and here it is 3EI by L because the far end is simply supported. And finally give the distribution factor next to the member representation. Okay, and calculate the fixed end moment value. Here the fixed end moment A to B is 0 because there is no loading, and B to C is 25, which is minus 25 and plus 25. Here the unbalanced moment 25 should be balanced to become 0 at joint B. So what is the procedure? We have to multiply the unbalanced moment with the distribution factor, that is 25 into 0.516 is minus 12.9 and 25 into 0.484 is minus 12.9. Here the span BA contains no load, hence the fixed end moment is 0 here. So that's why the summation of joint fixed end moment joint B to A and B to C is 25. It is 25 plus 0. Then the unbalanced moment is distributed for the span B to A and B to C by multiplying with the distribution factor. Okay. Next, the carryover should be done. Here B to A moment is here and B to C moment is here, and B to A it is fixed support and B to C it is a simply support. So the carryover should be done from B to A and it should not be done from B to C because of the simply support. So the carryover minus 12.9 divided by 2 is minus 6.45 should be added to the joint A, that is minus 6.45 we have to distribute to A joint, and here there is no carryover to the simply support condition. This unbalanced fixed end moment at joint C is further carried over here. In the simply supported condition, the moment should be equal to 0, but we have the moment minus 20. So if you note the joint fixed end moment value, the B has two values, minus plus 25, and C has another unbalanced moment of minus 25. First process is we are balancing the moment at B and try to make it the summation of moment at this joint is equal to 0. The second step is the pinned support moment, that is joint C. Joint A there is no fixed end moment. Joint B we are having the summation of fixed end moment. Joint C we are having the fixed end moment of minus 25. So at the simply supported condition, the moment should be equal to 0. So to make the moment here 0, minus 25 should be added with plus 25 plus 20. Then only it will become 0. And the distribution factor for the joint B, the distribution factor for the joint B comprising of two members, we are calculating with the stiffness value, and the distribution factor for the fixed support, end support is 0, and the distribution factor for the simply supported condition is equal to 1. So we are adding minus 25 and plus 25 to make 0 moment here. If you add plus 25, then this moment should be carried over to the nearby joint, that is C to B. The half of the moment is carried to the intermediate joint, so 12.5. Then this at this joint B, now the 12.5 is the unbalanced moment. Again this 12.5 should be multiplied with the distribution factor, so minus 6.05 and multiplied with 0.516 is minus 6.45. Then this minus 6.45 should be carried over to the nearby joint A, and this should not be carried over here because of the simply support. If you add these values, what are the values? 12.9, here we are doing the balance. No? So 12.9 plus 6.45 is minus 19.35, minus 12.1 and 12.5 minus 6.05 is equal to 19.35, and these two values to be added, totally minus 9.68 at joint A. Here we have balanced this minus 25 with the plus 25, so if you add these two values, it will become 0. So finally, we can justify the moment at simply supported point 0, and we have some moment value at A, and summation of moment at joint B equal to 0.